Our second presenter this afternoon and just prior to afternoon tea is Philip Guilfoyle. Philip's an industrial designer, been around for a while, and he's also now an independent consultant for the company Vintage Restoration Management. And I know that he's spending a great deal of time at the moment focusing on one spectacular vehicle that we've actually got here, very fortunate to have here in Australia. And I'm very rapt to actually have it here. I'm also an owner of a Delage, although mine has 9 horsepower, approximately the size of a small ride-on mower, a little bit different to the one you were about to talk about. So Philip is giving a case study on the 1914 Grand Prix car, Resurrecting, a sole survivor. Please welcome Philip Guilfoyle.
Just sort of get your undivided attention. Might do it. Can do it, yeah. This is what we're talking about. That's the 1914 Grand Prix Delage, the only one in the world, probably one of 4 that were made originally. It's the sole survivor, and that's what this case study is about. Yeah. Hang on, this might work. Sorry, I've got to open the PDF because font differences. That one? Okay. Righto. Well, I'm Phil Guilfoyle. I'm an industrial designer. I've been working in manufacturing in R&D with various manufacturing companies for quite a few years. Those companies include Victor, Lawnmowers, Sunbeam, Reen, Solar Heart, and Miller, the company that, in fact, I designed that fluid head and tripod camera sitting on in the back of the room many years ago. So being involved in new product development and R&D, I've been using digital technology since the early 1990s in the development of new products. And so what I want to do is to apply that digital technology to the restoration of vintage vehicles, which is my lifetime interest and passion. And what I'm doing today is presenting a case study. It's not really an academic research paper, it's a case study about the application of digital technology in the restoration of a rare and historic vehicle. You can see there, that's the vehicle we're talking about. It's the 1914 Grand Prix Delage car. I'll be giving you some historical background, some of the issues raised in the project, processes that we used, more technical side of things, and then some conclusions about it. And then hopefully at the end, if I have enough time, I'll talk about contextual issues which are really relevant to every restoration project. Okay, so Delage were a very prestigious, very successful sporting French top-end manufacturer, and in 1914 they developed a successor to their very successful Type Y which is called the Type S, and it was a totally radical car, and they fielded 3 of them for the 1914 French Grand Prix. Well, actually it wasn't the French Grand Prix, it was the Automobile Club of France Grand Prix, which was a premier event in July 1914. The cars didn't work, they were radical, they were totally new and weren't fully developed, but Mercedes-Benz won. But 30 days later, the First World War broke out, so that was the end of that racing season. And the cars were sent to the United States the following year. In this particular photo, you can see the 3 team cars that raced in that. The centre car, we believe, is the car that came out to Australia. And that's the right-hand picture there is a picture of the style of racing. It's road racing on dirt roads. That's what the car was designed for. One of the reasons why the car is so significant is it had many features that were radical and harbingers of the future technology used in automobiles. But I'll just run quickly through the specs. So it's 4.5 litres, cast iron engine block, had cross-flow head, 4 valves per cylinder, which is really pretty radical. Desmodromic, or desmodromic, depending on who you're reading. Valve gear, which means that the valves were mechanically opened and closed. It had 5-speed gearbox, which was unheard of in the day, and 4-wheel brakes, which was also unheard of. It produced 113 horsepower, which is quite a bit. It was quite efficient, it could do more than 100 miles per hour. And in that particular photo, you can see Louis Delage on the right. You can see Georges Léon Michelat on the left. He was the designer of the whole car, but also the engine. And the deliriously happy man in the middle is Duray, who was the works driver. In 1915, the cars went to the United States. The particular car that ended up in Australia was the car that belonged to Barney Oldfield, who was an extremely famous barnstorming showman of a racing driver and was successful, but possibly not the best driver of his era in the States. But the style of racing is completely different. It's the speedway board track racing, and you can see the track on the right there, which is an indication of the totally different style of racing. Anyway, it was a blood sport. Speedway racing in the United States was a blood sport, and it generated an enormous attrition rate. And the only thing to survive, the only one of all of these vehicles to survive, well, there were probably 4 vehicles plus some spares, and the only one to survive was Barney Oldfield's car. So that makes it, when you consider that the car was so technologically radical and a harbinger of technology that we really, some of which we only started adopting in the 60s and 70s, makes this car really quite significant. Now, the Delage came out to Australia around about 1923-4, not sure which, and won the inaugural meeting at Maroubra Speedway in Sydney in 1925. That's it on the right with the A on it, and I might tread on some toes in present company, but they're easily defeating 3 Vauxhall 3098s, including, I think, Boyd Edkins. Would Boyd Edkins be in there? It should be. Yeah. There's one of those, I can't read it from here. One of those guys is a very well-known name. Seems to be O'Rourke. Yeah, I think the guy, the second last card, the third card. Anyway, the car was eventually acquired by Lex Davidson, who, very significant Australian motor racer, had P3 Alphas, all sorts of stuff. He loved this Delage and got his hands on it, passed through the hands of some guys, a family called the Humes, And apparently one of the Hume boys got into terrible trouble at Melbourne Grammar for doing burnouts on the oval. Anyway, didn't get expelled, but was told to they never wanted to see the car again. Anyway, Lex Davison owned it. He's a 4-time Australian Grand Prix winner and an extremely significant figure in Australian motorsport. He did not restore it before his death in a race in 1969, I believe, but his widow, Diana, started the restoration of it in 1975, and it was acquired by Stuart Murdoch, who's a well-known collector motorist, or the whole family, the Murdoch family in Melbourne. And the restoration was meticulously completed under Stuart's guidance by Jack Nelson and Romsey. And it's absolutely magnificent, and it's acknowledged to be, by some, the finest veteran car in Australia. That, of course, is arguable, but it is absolutely magnificent. And, as I say, it's extremely unique. It embodies many groundbreaking innovations. It brings them together in one sophisticated package. The provenance of the car is extremely significant. It's a team car from one of the great marques at the beginning of the automotive era. It's performed in some very significant events on 3 continents, been driven by the best drivers on 3 continents of its day, and it's been owned by some very significant people, Lex Davison and possibly Harkness in the States. And I would even class Stuart Murdoch as a significant owner because of just the legacy that he has helped create. It's a sole remaining example. Of course, it's valuable. The Indianapolis Museum would love to get their hands on it. It's absolutely beautiful. And the thing that's really, really magic about this car, for me, is that it's driven. It's on the road. It's fully road registered, believe it or not. It's being driven. It's being taken to Rob Roy, used in hill climbs. The 4th generation Murdoch's been in it. The 3rd generation Murdoch's driven it. It's just a fantastic piece of heritage. It's here in Australia, surprisingly. In a funny kind of a way, it's almost a family car now. A very unusual one, but it's almost a family car. I should just point out, there's a bit more detail in my paper. One of the issues of significance with it is the fact that it's got desmodromic valve gear, which is quite radical. In my paper, in numerous books, like Automobile Quarterly and things like that, it's touted as the first Desmo valve gear. That's actually not true. Recently, a couple of 4 months ago or something, another Desmo engine, a 1909 engine, was uncovered. A very different single-cylinder thing. Anyway, what happened was the block failed. So the engine casting got a crack in it, and it could not be repaired. They tried laser welding, they tried metal spraying, they tried all sorts of things. And after 100 years, this thing stressed, cracked, corroded, all sorts of things. Any repair is going to, another failure is going to propagate next month or something. So Stuart decided to remanufacture the block, but it had to be exactly the same. No differences whatsoever. So you can see the casting failure on the right-hand side is a crack through the top of the combustion chamber on number 3. The issues to be addressed in the project had to be cost-effective. There's a market of 1 for this engine block. The provenance of the vehicle could not be destroyed in the process of repairing it. It's unique, so the only reference we had was the engine block. There's no drawings, there's no other block to reference at all, it's just one block. Precision. The remanufacture of the block had to be precise because it has to meet all the remaining parts, and those parts are precision, like crankshafts, camshafts, bevel drive housings, crankcases, all that stuff. So it's got to be perfect fit. It's got to be a clone. Has to be authentic, has to capture every detail. It has to be fit for purpose, because this car's a car that's driven on the road. It's driven. It's not a museum piece. It's not static. The processes we used, the sort of tech package I put together, was to laser scan the original block, build a virtual computer model of the original block, make some modifications to it, contraction allowances, machining allowances for surfaces that need to be machined away, design a printable sand mould for 3D sand printing process, print the sand mould, cast the block, and then machine the casting, reassemble the engine. The team that did this is Stuart Murdoch at the top, who's the owner, myself, the project manager, the premier restoration workshop, or one of them certainly in Australia would be Up the Creek Workshop in Castlemaine in Victoria. Keach 3D, they're a business in Bendigo, and they have an advanced manufacturer, well, Keach Australia, a big foundry in Bendigo, have an advanced manufacturing services division called Keach 3D, who have a relationship with CSIRO's Lab 22, which is a high-tech incubator for Australian businesses. So what Lab 22 do is they provide access to 3D printing machines for businesses, so that the businesses can train up, develop a business case for getting, or not, for getting their own high-tech 3D printing machines, and then go away and do it themselves. WYSIWYG 3D on the left, logo in the middle, they're the people that did the scanning, so they're a subcontractor. And VoxelJet, bottom left, they're the German manufacturers of the 3D printing machine. Now, what I want to stress is that what we are manufacturing here, we're capturing the information that is the engine, and we are developing a mould and 3D printing the mould. We're not printing the engine, we're printing the tool that makes the engine. And that tool is destroyed every single time you make a casting. So the original block was scanned with a laser scanner. That's the top left photo. It's a manual process, a bit like spray painting in a funny kind of way. And we developed a 3D solid model using scanned and solid modelled data. That's on the right-hand side. Computer, I presume, I can explain it maybe after the lecture if you need any things explained regarding 3D models or layered printing methodologies. We designed a sand mould, 14 parts as opposed to at least 42 in the original Delage factory casting. Now this is quite a different mould set to what originally would have been there. We used a 3D sand printer at CSIRO in Clayton, Victoria. The mould pieces are printed in batches, so you don't just print one at a time, you nest them together, and it's a cube of sand, and the printing happens with these individual parts of the mould embedded in the sand. So it's really quite an efficient process. It's a very efficient process, actually. It beats the hell out of pattern making, I'll tell you. Now, that's the two main parts of the mould, the 14-part mould set on the left there. They're very large, almost a metre long. And that's that's actually the water jacket casting. No, not casting, core, sorry. Coming out of the unprinted sand on the right. Then gets put into, so at the end of that, what you've got, when you assemble that, the bottom right picture there is a partly assembled mould set. And so at the end of it, what you've got is a sand mould, which is the same as what they had in 1914. It's a sand mould using foundry sand, furane binder. And the only thing that's different about what we've done is how we've acquired the specification through scanning, and how we've made the mould. But once the mould is made, everything's back to 1914 technology, basically. So we did a trial casting. That's it on the left and the original blocks on the right. We cut that casting up to look for problems and areas of improvement. Printed another mould set. I made a couple of changes. Printed another mould set. Did another casting. A little bit better this time. The first one was nearly perfect. This one was perfect. It really is fantastic. The job Keach did is brilliant. And we finished machining, and assembly starts, apart from a move of the premises, would have started last week. It's now starting next week. So reassembly of the Delage engine starts next week. It machined up perfectly. No voids, no nothing. So my conclusion to this are that what we've done as a project team is innovative, and it's the first time we know of that it's ever been done on a vintage car and all that sort of stuff. But because it's so efficient in time and money, it's just going to become standard practice. I can absolutely guarantee it. It's a real game changer for low volume, high value casting manufacture. And another point that's worth making is that this use of digital technology, once you've got the specification of the component, in this case it's the engine block, digitally recorded, you can do almost anything with it, and you can move off into other processes. That digital data can be used for CNC machining of conventional patterns. It can be used to make interactive virtual reality communication devices for museums. It can be used any way you like. It's fantastic. Oh, it can be used for, cast flow simulations. We did cast flow simulations and all that sort of stuff. So what the digital technology does is it lets you tap into the economies of scope that 3D printing provide, rather than be handcuffed to the economies of scale of the industrial age, where you're captive to the sort of remnant parts legacies of old factories spitting things out by the tens of thousands. You can literally build a one-off, provided the value of the vehicle can carry it. So the final part, to my definition, is as good as a clone. I think it's a real game changer, as I said. Now, there's a bunch of issues that you've got to I've had to sort of intellectualise in the process of this, and authenticity is a big issue in this particular project, and we're replacing a very, very significant part of a motor vehicle with a brand new part. And so you sort of get in that bit of an internal dialogue with yourself about what's authentic and what's not. There's been a big change in emphasis in the vintage car game, from the sort of perfect restorations as possibly best exemplified at Pebble Beach, these better than perfect restorations. The trend these days is towards sort of sympathetic, sensitive, oily rag type restorations where authenticity is everything. And there's a lot of focus on sort of barn finds and what have you. And in a way, it sort of, to my mind, sort of almost comes down to in a lot of cases comes down to not much more than taste. Old vehicles parts need to be replaced. I mean, obviously starting from the tyres, but through the life of a 100-year-old vehicle, they're never going to be 100% original. But where do how do you go about doing that and maintain the originality of it? So there's a lot of, at the moment, there's a lot of applied patina, that sort of thing, faux originality, and sometimes it's honesty and taste. It's where you draw the lines really in the eye of the beholder. Sometimes it can absolutely make a necessary new part fit into the landscape, I hate to use the word in the presence of an architect, but the landscape of the vehicle so that it looks right, and when it's actually deceptive. The life of the car is really part of the provenance. You know, the usage, the knocks and bumps and replacement parts are part of the provenance of the vehicle. I've got a whole thing. I'll skip the one on. Anyway, I'll go to my last slide. Static or driven. Collections are both can be a curse, but are generally a fantastic way of preserving our heritage. Display, like I prefer things to be on the road. I think it's as much as possible when possible, but there are instances where static display is entirely appropriate. And in this particular instance, being driven on the road is important for the Delage. It's the element where it should be, if at all possible, rather than a static thing in a museum, because ultimately cars are dynamic devices, and it's good to see that it's used that way still. So that's the Delage project. That's Stuart in the Delage in its element, driving it on a public road, probably a little bit too fast.
Thank you very much, Philip. It's another perfect example of Australians punching so much above their weight, both then, as Harriet pointed out, in the development of Repco and the Repco Brabham, and now with the work that we're doing here in Australia, which is as good as, if not better than the rest of the world. Any questions for Philip?
Thanks, Phil. Yeah, you give me great hope for most of my cars now. Thank you very much. My question is, having got all that digital data, scanning or whatever you said, the laser thing to get all that data, if there's a known fault in the engine, I'm speaking about one of my own cars here, if there's a known fault in that original engine that's 80 years old, can you tweak that digital data to, you can? Oh wow. I'm going to be in touch.
I'll use this one. Yes, you can. In fact, in the case of the Delage, there was a fault, which was probably known at the time in the original casting. I'm pretty sure it would have been known. Number 3 cylinder, the core, the sand core, had shifted and it created a locally thin wall section, and that's why it failed where it failed first, rather than at some other exhaust port. So we rectified that, and we made number 3 cylinder the same as the other 3, and it's easy to do, particularly in that instance because of the way that it was modelled. It was simply rectified. In actual fact, what we did was we substituted number 3 for another cylinder for number 3, and it's done because they're all supposed to be the same. And another, what did we do? There was another change. Oh yeah, there's a locally thin wall section in the casting, in the original casting, deliberately so. Well, maybe not actually intentionally so, but it was cast in, and we were concerned it wouldn't cast properly, perfectly, and so we just increased the fillet, just made it like you can't pick it, just so that it would cast better. But other than that, it's an authentic bone, and it had to be. The scan data, the resolution of the information you can get is extraordinary. You can pick up every little ding and stamp number and everything like that, but you can't replicate that sort of exactness in sand. So it's recorded in high resolution accuracy, but some of that resolution gets washed away in the sand, and so yeah. Oh, and project I'm working on at the moment is another cast iron engine block, and the owner of it wants to improve the performance of the engine, so we're changing the combustion chamber deliberately. But authenticity for him is not an issue. What's a faster car?
Interestingly, as I walk across to the next question, recent interaction I had with Shannon's is this is widespread insurance for classic cars with Shannon's. They are actually having active conversations. They had it with me about a claim for a part that VW couldn't give them. Right. And it's also something we're looking at within our partnerships that Simon and Liam and others have with insurance companies about the future proofing of insurance of automobiles and other sectors as well, using 3D technologies and the like.
Phil, thanks. Fascinating presentation. Just a couple of technical questions. What material did you cast it out of, and did you test the original and to try and match the same type of alloy? And I'm also fascinated. Normally, effectively you're using the original part as a mold, as a pattern. Normally, when you use a metal part as a pattern, you end up with a different size because the shrinkage in the cooling process in the mold. So, did you allow for those factors?
In this slide on the right-hand side, you can see how the top of the original blocks had a section removed. We used the piece of metal that came out of that section. That's trying to access the top of the combustion chamber to laser weld, unsuccessfully. We used that chip of material, had it spectro-analysed, and got a material composition recipe for it, and it basically turned out to be T250 cast iron. The purity levels of modern cast iron are better, but basically that's what, 0.3% copper and all that sort of stuff is basically T250. And just on modifications, we added 0.3% chrome. And the reason we did that is because we know that in a rebuild, the rings would be, we wanted the durability. So, so it's T250 plus 0.3% chrome. So, yes, we analysed the material. I did a presentation at the VSCC in Melbourne here some months ago. And one of the guys in the room said, did you ever think of taking the original block and melting it down and adding 10% or something and recasting it so it would be the original cast iron? And, like Stuart would have had a heart attack. But it's a really nice thought. You actually could do that. But, and now on the contraction allowance, Keach, the foundry people, the real experts, they're such an impressive team. They really are. They recommended 1% shrinkage. Yep. Which I was a bit sceptical of at first. It was too round a number, but it turned out to be absolutely crack on, like seriously accurate.
Because it can be a challenge. It's a real art.
Yeah. And so what we did was with the model of the block, we made it 1% bigger. So it gets bigger in length by breadth by height by wall section by 1%, universal. And then we use that model to then make the mould around. And so the contraction allowance is built into the tool. Am I drifting in and out of the mic?
No, you're good. Did you also have to put metal on in places to grind back and fill in threads?
Yeah, great question. Yes, we had to put machining allowance on all the machined surfaces. We generally work to 3 mil because initially we weren't too sure what happened. This is the first time any of us had ever done this. And we weren't too sure about the accuracy, so we wanted a little bit of leeway. 3 mil's probably too much in hindsight. So to every machined surface, say the base flange, certainly the bores, valve seats, all sorts of water jacket, manifold, any of those surfaces that are machined surfaces, we added a machining allowance, and you can see in this photo the there's no valve guide holes basically, so there's a big black surface along between the top of the motor and the exhaust or inlet manifold surface there. In reality, there's a whole bunch of valve guide holes there. So yes, we added in material that was destined to be machined away because it either needed the tolerance of a machined surface or the surface finish of a machined surface couldn't be cast.
One more question.
Yeah, hi Phil. I was just wondering, as a curator at the National Motor Museum, to do a project like this, it seems like you've got a team of quite a few highly technologically advanced companies working together, and it certainly is a very efficient process, but what would it cost the owner to do something like that? I mean, it seems like tens of thousands of dollars of consulting work type thing.
I can't talk about money specifically on this project. It was definitely done as a capped cost, and it's been done by all the parties concerned in a bit of a sort of a subsidised learning way. Certainly, all of us really have invested more than what would be considered commercial, usually in time, in fact always in time. And it's an expensive process. The value of the vehicle or steam engine or heritage manhole cover in a historic precinct in a city or whatever's going to be made using this process has got to be able to carry the cost burden of the process, and that can be in value. You know, the value of this vehicle more than covers the cost, or it could be an emotional thing. You know, it could be Lindsay Fox's first truck or something like that, and money doesn't matter. It's just worth doing. So it's got to be able to carry the cost. You said high price sort of consulting, engineering partners and all the rest of it. It is actually a very efficient process. The scanning is quite quick. It's a whole lot quicker than measuring up a block or anything like that. It's a quick process. The modelling that happens after that is relatively quick, and particularly with the efficiencies of modern 3D modelling programs these days and the skills of operators, it's quite quick. The printing's fast. Those blocks, those mould sets were 3-day print on the Vauxhall Jet. You know, at several $1,000s a day, that's still good value. It's a lot cheaper than pattern making and normal foundry costs. And then all the finishing and machining is the same as what it would be if it had been made by any other means. So there wasn't a lot, there was a fair bit of management in this project, but we've all learned and streamlined the process. It's just, you know, the second and the third job. On the third job now, it's all getting much smoother and faster and more efficient. Just quickly on cost, the crossover point between patterns and 3D printed sand moulds, you'd have no problem in 3D printing, say, you could safely say 25 mould sets cheaper than you could make a pattern and do conventional impressions and sand moulds.
Thanks, Philip.